The latest version of ProtoTwin includes some major usability improvements with brand new and exciting features. So let's dive right in. We've greatly improved the workflow for creating custom colliders in the software. In this model of a tray filling conveyor, I'll be demonstrating how seamless and powerful the new collider generation workflow is. Once we've added all of our components to the tray, we can run the simulation to see what happens. When the waffles fall, you will notice that they don't actually fall into the inside of the tray. This is because the physics collider we are using is convex, which creates a convex hull around the entire mesh. Similarly, if we swap the collider to a box collider, it will create a bounding box around the entire mesh, which isn't suitable either. The best option we have here to accurately represent the collision geometry of the tray is to use a custom collider. Previously, to do this, you would have had to export the individual mesh from the CAD software, import it into the collider tool, then export the generated collider from the tool and import it back into the application. Now, when you click Custom from the list, it will automatically upload the mesh for the tray, automatically open the collider tool, then download the mesh directly into the tool. At this point, you can generate your custom collider just like before. Once you're happy with how the collider looks, you can then click the Save button. This will automatically upload your collider and import it back into the application. If we run the simulation again, you will notice that the waffles now fall into the tray, just like we expect. We've added a brand new path move instruction to the robot controller component. Path moves are a common solution in robotics and manufacturing for automating tasks like welding, sanding, sealing, gluing, painting, and many more applications. Here we demonstrate a robotic welding application using the UFactory X-Arm 6-axis robot. Once you've added the path move instruction, you can select the curve for the path by hovering over a feature of the mesh and then clicking to confirm. You can also change the length of the path. It's only slightly too long here, so I'll fix this by reducing the length to 96%. You can drag the instruction in the list to move it. We want to perform the path move right after the welding signal is set to true. If we run the simulation, you will notice that the welding torch follows the path we selected. There's still a problem with this move though, since the torch intersects the right side of the workpiece. Make sure to reset the simulation before making further changes. One way to fix this issue is to change the orientation of the path. If we apply a 45-degree global offset rotation, you should notice the frames at the start and end of the line change to match this rotation. If you watch closely, you will now see the torch rotate 45 degrees so that it no longer collides with the side of the workpiece. Unfortunately, there's still a problem, since the torch now hits the end of the workpiece. We can fix this by applying a local rotation offset to the end of the path. I'll click the button to add a new local rotation offset, then select a percentage along the path at which to insert this new frame. I'll add a 45-degree rotation about the x-axis to ensure the torch is facing away from both sides of the workpiece. If we run the simulation again, you will notice that the orientation of the torch now smoothly interpolates between the start and end frames of the path. The robot no longer collides with either side of the workpiece, so the welding operation is now complete. We've added a number of utility functions to the robot controller component, which may be helpful if you want to create advanced scripted programs. In this example, I'll demonstrate the Move Linear to Intercept function, which can be used to move the robot to intercept a moving entity. I'll start off by adding a joint move instruction to the main program of the robot controller component. I'll select TP1 as the target, then select a solution from the list. If we run the simulation, you'll see that the robot performs a joint move to the desired target entity. Now we need to create a scripted program to execute the linear intercept move. The intercept target class we created needs to extend the robot program component, which will include an execute function. This function will be called by the robot controller when it tries to execute this scripted program. Here we want to call the move linear to intercept function on the robot controller component, which will command the robot controller to perform a linear move to intercept the target entity. I'll save the script, then swap back over to edit mode. Now I'll add our script to the parent entity, then select the moving target from the list of options. The last thing we need to do is add a call script instruction to the main program. Now I'll select the script we just added, which will instruct the robot controller to execute the scripted program. Notice how the robot now performs a linear move to intercept the moving entity, just like we intended. There are many more utility functions available, such as querying the time to perform a joint or linear move, solving the inverse kinematics, or getting the current joint parameters. In this last example, I'll demonstrate the use of the servo move instruction, which can be used to jog a joint of the robot. I'll go ahead and add another operation to the sequence to demonstrate the power of scripted programming. I'll first use the wait.seconds function, which will pause the execution of the program for half a second. After that, I'll add another servo move instruction. This time, I'll use it to jog the second joint of the robot to an angle of 45 degrees. If we swap back over to edit mode and run the simulation, you will see the first joint move just like before, then the second joint move after half a second delay.